So we were talking about the DSP processor, right? So we were mentioning about few features of DSP that may be helpful in case of implementing this type of image processing or machine learning based algorithms based on this image processing. So we have among common DSP features we have talked up to this. Now we are going to discuss about this memory and the DMA access. Let's start about DMA. DMA means the direct memory access. Okay. Now you think about your convolution layer, CNN. When you are doing, you have some input pixel details, input message related matrix, and on top of that, you are applying some filters, applying some weights, you can tell, and you are multiplying. So basically, this weight, maybe you have stored this image related matrix somewhere, but this weight, it is coming from your IO port. Okay. So always when you are fetching this inputs for you are actually this DMA, this type of access controls, these are meaningful when we basically work with huge input data related applications like our image processing related applications, image handling based ML related applications. So here through our IO port, you need to take huge number of inputs, huge number of weights maybe, because see you are working in embedded scenario. There your memory is also restricted. So you have huge matrix related to your input image. Along with that, you have large number of weights. Okay. Now it may happen due to your memory constraint, due to your area constraint, you are planning to do some optimization and you are not storing these weights always. What you are doing, you are taking this weights on the fly, you are doing this multiplications and you are sending the output for the next level processing. Okay. In this case, when you are taking this type of inputs, or some cases there are some applications when you are sending directly some view values to IO ports, the operations you are doing basically very similar. Each time you are taking some input value or you are passing some output value to this IO port. IO port means input output port. Okay. Now, as of now, you have the idea about how one instruction can get executed. When you are executing this type of instructions, that means fetch some value or store some value, load some value or store some value from IO port, then what will be the steps in general? In general, you have the CPU. There will be some request coming from the IO port that I want to store this value to particular register R1. Maybe from this register, your inputs will go to ALU, and from this input matrix related storage, your inputs will go to ALU, and then multiplication will take place. So in this scenario, basically repeatedly, what your CPU is doing, CPU is granting access to this IO port that yes, I am granting you, I am executing some instruction that will help you to store data from this IO port to this register. Repeatedly we are doing this because repeatedly we need some weight values coming from the IO port, and that need to be getting that should be multiplied with this input matrix. Now for this kind of similar operation, your CPU is busy. Okay. But CPU, when we are talking about the processing unit, CPU has some other function, other operations to do also. let's say the multiplication you are doing when you are getting some value from here and getting some value from where, that multiplication, or in pooling layer, whether it will do addition or the max calculation, or let's say you are doing some average pooling, the average computation, what type of operation it will select, that selection CPU, that instruction CPU should generate. But for this, when this during this input fetching phase, CPU is just busy to handling the same type of IO request and just sending the granting them, yes, you just fetch the take the value and put that in a particular register. That's all. That means CPU is just busy to doing similar executing similar types of instructions. Okay. Now this DMA, direct memory access, is some special kind of instruction or some special kind of solution to release CPU to release CPU so that CPU can get busy with some other meaningful work. Maybe at that same time, if there is another module, this DMA module is taking care of this IO request and just putting that value to the register file, nothing else, because this DMA is not not deciding which type of operation it will allow, or any opcode realization, or next what type of instructions will get executed by ALU, etc. All these things it is not taking care of. It is just taking IO input and putting some register value. So that is called the direct memory access, where we are releasing CPU to do this type of routine job and DMA will take control. Okay. So just see here in the slide, the feature that allows peripherals to access main memory without the intervention of the CPU. That means, of course, this IO value may go to some register or may go to some memory also. Okay. So this storage or loading or storing functionality is going on without the intervention of CPU. The main processing unit is free. Typically, the CPU initiates DMA transfer. That means when IO is first requesting, it will first take the permission from CPU, and once this permission is granted, CPU is free. That's why CPU initiates DMA transfer, does other operations while the transfer is in progress. So this is also, you can think, one sort of parallel processing. One processing, DMA is taking care of this input-output transfer processing, and CPU is taking some kind of ALU processing. Okay, and receives an interrupt. We will talk this interrupt later. Maybe interrupt from the DMA controller once the operation is complete. Interrupt here, you can think one signal. So DMA controller will send the CPU the information, the notification. Yes, now the IO transfer is complete. Okay. Okay. Now you just leave this term cache coherency problem. We will talk that later on when we talk about the cache memory, etc. Now, request DMA controller, of course, DMA direct memory access is controlled by this particular module that is called DMA controller. Okay. So here in this diagram, you can see this IO port is basically connected through this DMA controller and directly loading or storing data through to and from this memory. There is no intervention of CPU from microprocessor. Okay. Now we'll look a bit. We will see in detail a bit this the concept of this DMA access. So how this DMA controller looks like. Okay. You can see there are few signals associated with this DMA controller. Okay. Or you can think about these are a few pins. Okay, containing some signals, generating some interrupts, or giving some address related information. Okay. Tally with this left side diagram with the right side one. You can see here you have this CPU, you have this DMA, you have this RAM and this IO device. Okay. So first, as we mentioned, this IO device will request, okay, that there is a request coming from IO device. One second, please. And there will be some acknowledgement of that request. Okay. So you can see here, there is some DMA request, okay, coming from IO device, and there is some acknowledgement. This is a bit, I mean, just ignore this one. This will be this direction and this will be this direction. Okay. So IO device will send that DMA request. Okay. And there will be some DMA acknowledgement. Once that DMA acknowledgement is given by the DMA controller, that request will go to this by this, see this bus request and this bus grant. These are two pins. So this, when this bus request, this pin is high. Here also the same pin you can see. This is the control logic. When this bus request pin is high, that means DMA is sending a request to CPU that now the bus, this, you can come back here to this diagram. This bus request, that means now I will directly transfer data from IO device to the memory. So no intervention of CPU is required. So now the DMA controller will take hold, and for that, that bus request is met. That means this pin is set high, so that CPU will understand, okay, now there is a one request for granting the bus. When CPU is allowing this direct memory access, these pin will set high, bus grant. That means, okay, the CPU is allowing that now DMA controller will control the bus, and according to that, according to the given inputs coming from the DMA controller, data transfer will take place. Fine. Once that bus grant is given to DMA controller, next part is easy. So next part is you have to give the information about the address and select the register also from where the data will come and in which address it will reside. Okay. So that address and accordingly the selections. Okay. You can see here that address and selections will directly go to this RAM. Okay. Read or write part of this RAM. So here, when let's say the DMA can hold good for both the cases. When you are copying some data from RAM to your output device, or you are fetching some data, storing some data from input to your memory or your RAM. In both the cases, DMA access is possible. So that means when bus grant is made, after that, two possibilities are there based on based on your application. If you are now trying to write some value coming from your IO device and you are trying to write that to RAM, so accordingly, this read or write select signal will be high. Once one of the signals are high, maybe it is write signal because now you want to write some data to RAM. Once it is high, next, based on the address input given, you will select which part of RAM you are going to write. What is the destination address? So you are getting the address, you are getting the idea what to do. Should I read or should I write? Then you are placing the data there. Once write select input is high. On the other hand, or on the reverse, if you are now trying to read some data from this RAM and through DMA, it is coming to your IO device, that means this read input will be high. This read input will give the idea to RAM that, okay, there's some operation is going on, application is going on, which is reading data from RAM. Now RAM is a big space. which part of RAM. So address will give the idea that from this address to this address, the data will be fetched, and then the data from this data channel, it will get passed through this DMA controller. It will get passed, or it will be directed, channelized to this IO device. So, and in this whole process, after this bus grant has been done, CPU is not at all intervening in this process. CPU is free to control other operations. Okay, so that is the advantage of DMA, and that is heavily used in these type of data centric applications, where you need to incorporate, you need to fetch huge amount of data from your IO, and then on top of that you have to do the processing. Okay, so this DMA access, DMA controller is one of the helpful feature that is present in DSP processor also, and that is meaningful for our this image processing scenario, or this type of next convolution. But actually, when you are not planning to store all the weights, you are not having enough memories to store all the weights, as well as store the whole input matrix together in the memory and then process it. So you are just storing one of them, and another one you are taking at the runtime, and you are processing on them. So that way you are saving in terms of memory. Also, you are saving in terms of processing time, because in parallel, two types of operations are going on. One of this DMA controller is helping to store data coming from IO to RAM, and at that time maybe CPU is focusing on the multiplication part, or maybe in case of average computation, max computation, if you are in the pooling layer. So that way CPU is doing some other job. So this is the basic idea of DMA. Is it clear? Is it clear?
Yes, ma'am.
Okay. So this is one feature of DSP. Next, we talk about the cache memory. Okay. What do we mean by this cache? There is different cache means this is a smaller storage. We have so far we're just talking about memory, and we know that whenever we are processing something in the ALU, we are fetching data from somewhere. Okay, and that is our storage, and that is in general that is our memory. But memory fetch and memory write, those are very costly. Okay, costly in terms of required number of clock cycles, in terms of performance. Okay, the reason is that you can simply understand memory is huge. You have some you need to have in your microprocessor or in your microcontroller, you have to keep some significant amount of memory, right? So you have some large number of memory blocks, and somewhere your data is residing. So you have some address knowledge of that address space knowledge of that memory block. So you are based on that address, from that address you are fetching the data and you are sending that to ALU. Now you think that address, a particular, you are basically what to say, wasting some time, we can tell, wasting some time to get a particular memory, to identify a particular memory block, and then to fetch data from that memory block. That requires a significant amount of time, and that's why memory read and write is costly. Whereas if you just put a smaller memory unit, okay, type of first and relatively small memory, the size is small, that means number of blocks are small, lesser. So whenever you are searching for at the first, not only in this type of memory, not only the search is less, but also the underlying components that we are using to create this type of memory, this faster memory, those are also different. Those are also costly materials in terms of fabrication, in terms of designing. But I'm not going to that detail. What I mean to say, this is first of all, this is smaller in size, so relatively for search. And also, this is some way component wise also this is costly memory. So with all this, they are allowing for search also. So that way, this memory is a type of fast, relatively small memory, and this is sitting between your actual memory, your actual storage, and between your ALU. Okay. Of course, we other than this, okay, these are the hierarchies. We will talk about this later. But other than this cache memory, the fastest form of memory is register. Okay. But this is costly, and this register, whenever you see your any we have seen the architecture of DSP processor or any process architecture, you see the number of registers, those are very less, and this register storage is also very costly, so we cannot support much number of registers in our process. Whereas the this cache memory sitting between, maybe you can think between this register and your actual memory storage, and it is faster than your memory, but not so costly as we I mean as the cost we get it register. So this is the hierarchy from ALU to register, really to this cache hierarchy, and then your actual memory or main memory. Now, quickly, how you are placing your data in your cache memory. Okay, based on the support you are getting from your underlying processor, that means how many numbers of cache or cache layers you are having. Based on that, you can actually calculate your gain or the performance requirement of your the prediction time. Whenever you are doing the prediction, you can think that you have to handle the fully connected layer. So there are lots of multiplications. And if each time for that multiplication, your weight, as we have seen here, it was stored coming from your IO device, it is getting stored in this memory, this RAM port. Every time you are accessing RAM, you are fetching the single weight and you are multiplying. Then only you can do one step of your convolution computation. That is your really a costly requirement, and that's why in between we have stored this type of smaller cache memories. And what we are doing, we are in that cache, we are storing the weights that we are going to use frequently. Okay, we will talk this part, maybe we can skip as of now. We will talk in detail when we talk more about the algorithm optimization, where there we will see how we can arrange our convolution steps itself, so that we can get a better advantage in terms of whatever data I have in the cache. Why? The meaning of this is, whenever, see, you have your main memory of a larger size, you have cache of a smaller size. So it is not possible that you can map all the blocks to this smaller memory at the same time. If you have some n blocks, you should have some m blocks here, whereas this m should be much smaller than n, right? Now to do so, what you have to do, you should have some algorithm that is choosing of which blocks you will actually map, or you will actually bring to this smaller memory, and which block will be left back into the main memory. But what will happen if you need some data from this block left in the main memory? Because every time your ALU is fetching data from here, it is making a request here and it is fetching data from here, correct? Now, if it is requesting some data from coming from this block, and this block is not present in this cache. So what will happen? That we term it as cache miss. Okay. Block is not mapped to the smaller memory. So if you see, this is your memory. This is not large number of blocks present, whereas in your smaller memory, you have smaller number of blocks present. So multiple blocks of your main memory is basically getting mapped to same cache location. Okay. So there is a chance when a particular block is residing in that smaller memory location, other blocks, they are not present in the main memory. And if you are trying to fetch any data from that other blocks, that of course in turn lead to a cache miss. Okay. Whereas the cache hit is straightforward. You have requested, ALU has requested something from the smaller memory and the block is already there. You have already fetched the block from your main memory. If that is the situation, then there will be a hit. That means block is mapped and return data access is successful. Okay. So these are the two terms, this hit and miss. Okay. Now, when we are talking about this hit and miss, that means we have to understand how our block is getting mapped. We'll quickly see this. There are three types of mapping. One is fully associative mapping. One is direct mapped. Okay. One is state associative map. Now, this fully associative are direct map. These are two reverse situations, opposite situations. Okay. So in case of fully associative mapping, the idea is, let's say you have some number of blocks, these 12 blocks, they can go anywhere. Okay. Whereas in direct maps, block 12, a particular block of a memory, can only go to a block 4 or a particular number. Okay. We are basically taking the some mod operation, or there are different algorithms, no need to understand as of now. Just to understand that what about a particular memory block. One idea is you take this memory block and place wherever any block is free, or wherever any place is free in the smaller memory. This is one idea. Another idea is you take this block and always fix that this block, if the block number is 4, this fourth block will go to a particular location of this smaller memory. So these are two opposite situations. And when we are considering this, we have I mean, there is always some pros and cons of every choice. Okay. So when we are choosing that this memory block can go to any place of this smaller memory. That means when you have to search for the data coming from the block, you have to search in this overall memory, I mean overall cache memory. Whereas if you have some mapping technique that a particular block can actually reside to another particular block of this cache memory, then the flip side is that when that location is full, maybe you have A, B, C, D. These 4 blocks, they all can get mapped to a particular block, maybe some C, E block of your this cache memory. Now, if the C block is filled by A, then and you are requesting some data from B, C, and D, there will be constantly some miss, because when you are trying to access this C, you are getting that A is there and B is not there. So whenever you are trying to access some data from B, what you have to do? You have to replace A from the cache memory. You have to bring the B back there, and then you can access. So repeatedly, there is a concept of hit and miss. So that's all. That's why we generally talk about this solution, this state associative mapping, where we keep a window. We do not fix that, okay, this block can go to a particular frame or particular location of the smaller memory. No, we are putting a window that, or again, we are not so flexible that one memory block will just go to a or to any one of the cache memory blocks. We are putting a window that, okay, let's fix these four blocks of the cache memory. And this A or B, they can get mapped to any one of these four blocks. So this is called state associative mapping, where we are making a state, and within that set, anywhere one block can be placed. Okay. So the idea is you have some cache memory support in DSP processor that is helping. So there are different levels. Okay. First, you have a very small cache, then that small cache is searching in a comparatively larger cache. Then from L1 to L2, it is going to that more bigger cache. So that way, this is the hierarchy. You can, the more you form the hierarchy, the more you understand. There is, of course, there are some pros and some cons. That when you are searching at the L0 cache and you are getting the data, this is very fine. Of course, that there the time of a hit, the time of fetching a data is very less. But where is the flip side? If you are considering very small cache at the initial level, there is a possibility that there are very small number of blocks, right? So that small number of blocks basically holding small amount of data, small number of memory blocks at a time getting mapped from the main memory. So in that way, there is a possibility of cache miss, high possibility of cache miss. So there should be some particular size requirement how we are designing that, but we are not going to that cache related algorithm. Just we are giving the idea that in our DSP processor we have this cache memory support, smaller, faster cache, where we can store some weights. Those weights we are using frequently. Now you think about your convolution, example. How this is meaningful. When you are doing the multiplication or you have this type of input matrix, okay, you have some filter. 1 2 3 1 2 3. Okay, you are multiplying. Okay, you are multiplying, and then you have the concept of stride. You are shifting the location of the same filter, and you are multiplying again and again. Okay. Now you think the scenario, if you have that means your ALU is doing this multiplication here. Multiplication is going on in the ALU. Now this filter weights, if you store in your L0 cache or any L1, L2 cache, because you are repeatedly at a particular time, you are repeatedly fetching the same values, some and repeatedly or fetching the similar values, and you are doing the multiplication. If that is the case, if you are storing these values in the cache instead of storing them in the main memory, where this fetching time will be high, or fetch or memory write back time both are very high. Rather than that, if you are using cache to store this type of filter value, that will save some time in terms of memory fetching, getting the input, and then doing the multiplication. So this is the importance of cache memory that is heavily exploited when we do this type of filter operations with the striding. We are shifting these filters and doing repetitive multiplications. Is it okay? Is it this part clear? Why we need this cache memory, or how this presence of cache memory is helping us doing this multiplication faster? Is it okay? Or
Yes, ma'am.
okay. So this is the concept, or this is where we are using the cache memory, or the feature this cache memory is meaningful. Okay. Another basic, maybe this whatever we have discussed so far, this cache memory or this type of DMA processors, you can find this in other type of processors also, because these are very meaningful whenever we are trying to do something repeatedly, or we're trying to use some inputs repeatedly, or we need some we have some requirement or some application to transfer data directly from IO to the processor. These are very common processor features. But one typical feature that is very unique to DSP processor is the usage of this circular buffer. Okay. The memory is arranged in a circular fashion. Okay. What does it mean? Why it is important? First of all, you think we are doing in case of our signal processing also, or we in case of our this convolution related operation also. We have already seen the analogy in our first slide. So we are doing some kind of this type of multiplication. Okay. Now if you are doing you are having some weight, and you are multiplying that with some value, and you are gradually proceeding. You have allocated some memory for this weight, and or AI, maybe here you have taken AI, and you have allocated some value for xn minus 1. Okay. So AI and xn minus I. You have allocated some value for them when I is equal to 0. You are having some value. I is gradually increasing, and you are just getting xn minus 1, xn minus 2, and so on. And also A0, A1, A2, and so on. At some point, this A0 or A1, it is not any, it is of, I mean, it is not very much meaningful to you. As you are proceeding, basically, once you are processing xn minus, let's say 55, that time xn minus 0, that is of no value. But if you are actually allocating your memory in a linear fashion, like you are storing this way, a0 xn, a1 xn minus 1, and so on. So gradually, whenever this part is not, this data is not getting used, still they are filling some place. Still they are wasting some place. But where memory place, memory blocks, you can think. But this is not desired. In our case, we are always working in a very constrained scenario. So we want to reuse those memory places. And how it is possible? This is possible. That's why whenever we see the arrangement of memory blocks in DSP processor, it follows this kind of circular buffer concept. That means you have started maybe some location of this circular buffer, and you are proceeding in this way. So after some window, you are again reusing this place, and at that place, at that time, maybe the data that you have previously stored in that memory block is of no use. Okay. So that means this is a very important concept. This the circular buffer. We are reusing the memory space as those the memory arrangement, memory blocks are arranged in a circular way. Whereas in general implementation, we allocate memory as a form of array, or in a linear manner, like this. These way blocks are arranged. So here, reusing some block, for that you have to traverse the whole length Then again you can come back here, you can again reuse this block, then this block, then this block, and so on. Whereas in the circular buffer fashion representation of memory, reusing these blocks, that is quite easy. Okay, so that's what exactly it is written. A better approach is to use a circular buffer where an array in memory is interpreted as having a ring like structure. An array in memory is interpreted as having okay, sorry, it's a repetition, I will remove. So you are having a ring like structure. So after a certain window, basically this ring like structure is useful to reuse your previous memory block. Okay, this is one feature. Now when you are trying to reuse some blocks of, or you are trying to access this ring like memory blocks, ring like arrangement, so the addressing is also not so straightforward. Here we consider a bit reverse addressing. What we mean by this, you can observe. You just, this is just for your knowledge. You can, understand that the address calculation in general, what we do, we have some address, maybe 0000. The next address we add some value, maybe +2, and we do it 0010 or something. That way we are getting the next address. That way when we do that in a linear fashion, linear increase of our address. But here we consider bit reverse addressing. You can see the arrangement. If this is your starting address, and instead of adding 2 means the representation is 010. Okay, you are representing it, you are adding this, the bit, the one, you are adding one, but in bit reverse way. See, you are always adding 100. So you are adding one in a bit reverse way. That's why it is bit reverse addressing. So what will be your next address? It will be 100. Next 100 plus again 100, 010, 110. If you go and proceed so on, at this stage, at the last stage, what will happen? This 111 plus 100. Okay. Now, if you discard some carry, you will get this 000. You can calculate by your own. You will get this idea. That is, when you are adding, generally, if we want to traverse to the next address in our linear array fashion, we add some number. We may add 001, 002, and we can traverse to next address. But here we are taking a bit reverse representation of addressing. Here we are taking 100, we are adding, we are getting these values. So what is the advantage? At the end, we are again getting back the address all 0. See this one, this address. This is the address we are getting back. So we have started from all 0. Then we have increased, we have stored our data, we have accessed the particular memory locations, we have stored our data there. Again, after, at the end, after a few steps, we are coming back to all 0. So I think with this, it just, this type of addressing, it justifies the implementation of ring-like structure. Ring-like means you have started from this location with all 0. You have traversed the next location with addition plus 100. That way you traverse all your locations, this, and so on. And then you have came back to all 1. And with again addition with that same 100, you are coming back and you are reusing this all 0 location. Okay. So to implement this circular buffer scenario or circular ring-like memory, you need this type of bit reverse addressing. Okay. So this is very important feature, that is saving your memory. You are not in your linear representation of memory. If you just increase your memory indexing, directly, memory address directly with one or with two and with any index. So what will happen at a particular point of time, the list will go long, the value will go long. And then again, if you want to come back to your initial position and you want to reuse some memory location, you have to basically backtrack a lot. To avoid that scenario, to DSP supports this type of efficient addressing technique where we are just the address calculation is done in a specific way, and address calculation is done in this beat reversed way, where we can actually get the idea how we are accessing the locations of this ring like structure. We are starting from a particular location and we are coming back there. Okay, so this is a special feature to support efficient implementation of FFT algorithms. FFT means these type kind of algorithms. And from our first slide where we have discussed the analogy of with our DSP processors, we know that our actual convolution implementations, we can go back a bit. Where we have started, we have seen that these representations, it is very similar to our FFT implementation. Sorry. Here we have discussed about the analogy where we have seen this one multiplication and one accumulate. The same type of operation we want to do in our signal processing scenario and in our image processing or this convolution processing scenario also. Okay. So this type of memory arrangement is very meaningful in both the cases. So with this, we mostly discussed about our related. There are many other features of DSP, but we have just discussed what are required for our purpose. Next day, we will again talk about some machine learning algorithms, vacant sleep algorithm, etc. We will start with that, and we will see some demo also with that vacant sleep algorithm. But whenever you will see some algorithmic steps or operation steps of your learning algorithm, you can directly map to these kind of components, your processor components, and you can understand. I hope you can gradually, if you think, you can understand why these features are given to the processors and what are their purpose to bit to for efficient execution of your top level algorithm. Okay. So I think with this we have discussed about cache, we have discussed about a bit about DMA and other DSP memory organizations. Okay. If you have any question, you can ask me. Any question?
Ma'am, that bit reverse addressing mechanism in that. So here, how many address bits are there in that?
It's like this. Like this. It is with this 3-bit representation. It is shown, but you can extend it. No problem. You can extend it, and you can check that with that when you extend those bits, this number of steps will increase, and number of more locations. I mean, you will get the support of more number of locations in your memory.
It is when window size will increase.
Window size will increase when you will based on your when you want to reuse how many based on it. You can think this way. You can based on your filter size also. If you are using the one filter repeatedly, if it is a 3x3 filter, basically it's the 9 values. If you store and you are processing them, then after that you can actually come back to the previous location and you can reuse. I mean reset those values with some other filter values, right? Whereas if you are going for 5x5, this window size the requirement will be more. Correct.
Yes, ma'am. Ma'am,
But
here,
yeah.
here we can see that 4 is added. 100, that means 4 is being
Yes,
added.
yes, yes. But the concept is why we are talking, telling it beat reverse. In general, what is the concept? I have some, when you, our traditional processors I have one address location, some address A, then I add A plus 1, that is my next location. That is my traditional concept of implementing what to say, the processor addressing. But here see, we are just except 001, we are actually bit reversing and we are adding 100, and that way we are gaining in this term of this, we are getting the addressing idea about this wing access, we are getting the access of this wing length representation. That's why bit reference. Okay,
Okay.
you can see the this. Anything else, others? So everything is clear, no problem.
Yes, ma'am.
Okay, just go through this part, and maybe for some of you this processor related this concepts are not so common. So I think you can refer to this book. This is a, yeah, this book I have added here also. So you will get some PDF, online PDF also of this book. So whenever you are having this, having any doubt about this processor related these structures, or because this uh, ring-like representation or bit reversing, that is very specific to DSP. But for other, this cache, this pipelining, if you have any doubt, you can refer to this. It's very helpful. If you have any question, maybe next day also, you can ask me. And this is one. This is okay. One part is there. So from this is self-explanatory. You can get go by your own. What is the difference between DSP and versus microcontroller? This is one example. It is shown the basic architecture, what you have in your DSP processor. This is just for you can just look into this slide after this part. You have this type of this JTAG. This is for communication, and so this is for debugging also. Okay, and other than that, everything I think you will understand. Just what are the components here? No need to remember. From this slide, don't worry, there will be nothing in the exam or something. This is just to show you how this one DSP architecture. So far, we have talked so many things. So how they are arranged and how they look like. Okay. So these are the basic components of a DSP processor. But we will not be talking about much about DSP processor. We will be mostly focusing on the machine learning algorithms. And we have talked some, there are many blocks you can see, I have skipped them. We are not talking here mostly about DSP processor because we're talking about machine learning algorithms. So we have talked as much as that is required to enhance the performance or implementation of our machine learning algorithm, or that type of CNN blocks, convolution block. Basically, we have mostly focused on that convolution block because that is the most costly part, and that takes 90% of computation overhead. So, but this is for your general knowledge how they are arranged. You can, okay. So that's all from my part as of now. If you have no more questions, you may leave. Maybe next day, if you want to ask anything else on the CSP part, you can ask.
Thank you, ma'am.
Thank you.
Hello, ma'am.